Good day and welcome to AFD'S Academy. I am Acho Francis Deban. Today, we're still going to continue from where we stopped in our previous class, which is basically calculations in volumetric analysis, cutting across percentage purity and maybe some few questions in water of crystallization. And also a little touch in the Redox titration calculations. So I'm going to just go ahead and do the needful. So in our previous classes, I've given us the formulas for volumetric analysis, all of them, including the percentage purity and water of crystallization. This is essential if you can remember them and make good use of them. So today we're just going to use those formulas like I've given to us to solve certain questions and see how that goes with us. I only believe that what we're doing here, we'll be able to remember them when the time comes. And it is important that when you practice all the time, this thing become part of you. So I will urge you to always go through the videos. For those of you who have not subscribed, you subscribe and like the videos equally, and also your notification bell. So whenever I make an upload, you're going to see it. So let's start with our first question. I will read it, then this start the given, then we'll move on. We say 12 grams of a mixture of anhydrous sodium triisocarbonate 4, which is Na2CO3, and sodium chloride. So it's a mixture, which means it is impure. What we're looking at here is sodium triisocarbonate 4, but there is some particles of sodium chloride. That sodium chloride is the impurity therein. They say that were made up to 1 dm cube of aqueous solution. So 25 of this mixture were neutralized by 20 of 0.2 mole hydrochloric acid. We should calculate the mass of the sodium chloride impurity. Find also the percentage purity of the triisocarbonate 4. So we're going to look at the percentage impurity and that of purity. So that's what we're going to do right now. So I'm going to list out the given and we solve them. So here we have the acids, which is HCl, and we have the base B, which is Na2CO3. We say that of sodium triisocarbonate 4, we have 12 grams of the impure sample. So percentage mass ton of impure, let me call it GDM cube of impure is 12 grams per dm cube. Okay, now we say 25 of this mixture were neutralized by 20 of A. So the volume of the base, VB, here is 25, while the volume of the acid is 20 cm cube, and the concentration of the acid is 0.2 mole per dm cube. Now, we should calculate the mass of the sodium chloride impurity and then find also the percentage purity of the triisocarbonate 4. Alright, so from here we have to balance our equation, then we proceed further. We have the number of moles of acids and the number of moles of base. This is in cm cube, but we can only get that when we balance our equation. We have our HCl plus Na2CO3, which gives us sodium chloride plus water plus CO2. Although this is liquid, this is gas, this is aqueous. Now, the question is our question balanced? We have to find out. We have 1 sodium, but here we have 2 sodium. So I can equally say I have 2 sodium. Now, if I have 2 sodium, I have 2 chlorine now. Here, there's 1 chlorine. I can still put my 2 here. I have 2 chlorine, 2 chlorine, 2 sodium, 2 sodium. That's balanced. Hydrogen is 2 now. Hydrogen is 2. Oxygen is 3. Oxygen is 3. So now our equation is balanced. And the number of moles of acid is 2 here. And the number of moles of base is 1. Now, for us to be able to solve the percentage purity and impurity and all of that, we will be able to get the mass concentration of the pure sodium carbonate 4 first, because it is required. For percentage purity, it says that the formula is the mass count of pure over impure times 100. Why? Percentage impurity states that mass count of impure minus pure over impure times 100, which means it is essential that we get the mass concentration of what? The pure, before we can do any of that. Now, we want to get the mass count of the pure sodium carbonate 4. Now, how do we do that? For us to do that, remember the formulas. Mass count is molar count times relative molecular mass. And the molar count of the base is not given, so which means then we have to calculate the molar concentration of the base first before we can proceed to do any other thing. So let me call it here Cb, which is the concentration of the base. We will look for it. So for us to do that, we use our CAVA formula to get that. So let's say 1 to get the molar count of B, we use the formula CAVA over CBVB is equals to NA over NB. And we're looking for CB, so my CB is equals to CAVA over VBNA. And this is equals to, my Ca is 0.2 mole per dm³ times volume of the acid is 20 cm³ times number of moles of the base Nb is 1 all over volume of the base is 25 cm³ times number of moles of the acid Na is 2. So we check from our calculator here to see what we get. I have 0.2 times 20 divided by 50, 0.08. So our answer is 0.08 mole per dm³. Now, if this is our Cb, which is 0.08 mole per dm³, the next question now is for us to get the percentage, the mass concentration of pure sodium carbonate 4. They've given us that of impure. And from our analogy, we said that the mass count of the pure must be lower than that of the impure. If it is not so, it's either we are wrong or there is a mistake in the question. So let's believe that when we go through, we're going to get that. So this is 12. We want to find out of what? The pure sodium carbonate 4. That's the mass concentration. So I'm going to take this out so that we'll be able to do that calculation. Now, 2 mass count of pure B. We can get that by saying this is equals to molar count of B times relative molecular mass of B. The molar count is 0.08 mole per dm³ times the relative molecular mass of base This is 23 times 2 plus carbon is 12 plus oxygen is 16 times 3. So I have my 0.08 mole per dm cube. This is in G mole. Now this is 46 times 46 plus 12 plus 48. 40, 40, 80, 90, 106. So I have 0.08 mole per dm cube times 106 G mole. This is equals to times 106 is 8.48. This gives us 8.48 GDM cube of pure B. So this is the GDM cube of pure, which is 8.48. So from the analogy I gave us, it is true that the mass count of pure B is lower than that of the impure. So if we have base, then we can just proceed further to solve the percentage purity and the percentage impurity. What did they ask us to do? Say we should find out the percentage purity and that of impurity. So let's begin. Let me clean this out. So we've gotten that. I can clean the board now. Now the next thing here, 3, says percentage impurity is equals to what? Now I gave us two formulas which were statutory. Those ones are fixed. And I now gave us another formula which was not captured in the formulas which I gave us, but we can use here use that here. Let's see how that works. I say percentage impurity is mass count of impure minus mass count of pure over mass count of impure times 100. So the mass count of impure is 12 minus 8.48 over 12 times 100. And this is equals to what? Let's see. 8.48, good. 12 minus 8.48 divided by 12 times 100 is 29.3. 29.3% impurity. So if this is percentage impurity, we've gotten our fourth answer, which is 29.3%. Remember, I gave us also a formula that says percentage purity plus percentage impurity is equal to 100, which means 100 minus 29.3 will give us our answer, the percentage what? Purity. So I can easily just use my calculator now and minus 100. So my percentage purity becomes 70.7. That is simple as that. If you want to use the formula, you put in the formula. Or better still, if you want to use the other formula that say mass count of pure over the mass count of impure times 100, you still get that. But okay, let's try that one. Percentage purity, which is mass count of pure over mass count of impure times 100. So if I take these ones out, let's see how that is true. Now I can now say mass con of pure is 8.48. 8.48 over mass con of impure, which is 12 times 100. And this is equals to, so I have my 8.48 divided by 12 times 100. 70.7. So it's still the same. We have our 70.7% pure. So any of these, you should be able to use any of these formulas. You achieve or get what you want very fast. And it is important when you're versed in your formulas principles, with your formula principles, you can easily maneuver yourself, no matter how tight the situation may look. And off you go. You're going to be fine. So let's take another question based on percentage what? Purity and impurity. We say A is 0.100 mole per DNQ hydrochloric acid. B contains 6 grams of a mixture of anhydrous sodium triacylcarbonate 4 and sodium chloride. This is also a mixture, which means this is the mass concentration of the impure in 1 dm cube of solution. 25 cm cube portions of B required an average of 22.65 cm of A for complete neutralization. From the above data, calculate amount in moles of sodium carbonate in 1 dm cube of B. Okay, when we say amount in 1 dm cube, now this is the question. Listen, this is very important. You will see that. You say amount in 1 dm cube of B. Now, what exactly are they asking? They are not asking you to calculate the amount. That is not it. They are asking you for the molar concentration. Why? Amount is in mole per 1 dm cube. dm cube. That is what they are asking you. So they are asking you to calculate the molar concentration, not amount. So when you see amount in 1 dm cube, they are requiring you to do what? Calculate the mole per dm cube. All right? So take note of that. It is a tricky question. So let me clean the board and list out again. All right. The acid is HCl sodium triacylcarbonate 4. Okay. Okay, the same. Now let's take the given. A is 0.1. Ca is 0.100 mole per dm cube. Okay, B contains 6 grams of a mixture. B contains mass con of impure. Mass con of impure 6.0 gram per dm cube. All right. We say 6 grams of a mixture of anhydrous sodium triacylcarbonate 4, okay, and sodium chloride in 1 dm cube. Good. 25 of B required an average of 22.65. VA is 22.65 cm cube and VB is 25 cm cube. Okay, what again? From the data we should calculate. Now they've given us everything which we need. Now, for us to proceed, we have to still balance our equation to get the number of moles of acid and the number of moles of base. So that with that, we will be able to use the CAVA formula to get the concentration of the acid in mole per dm cube. So now let's say I balance this equation because we use the same variables. So I don't want to balance it no more because it's the same thing. Here is 2 and my MB is 1. So with this, let's see, we can do that. For us to get number 1, molar con of B, we use the formula CAVA over CBVB is equals to NA over NB. And we're looking for the CB, so CB is equals to CAVANB over VBNE. And this is equals to CA is 0.100 mole per dm times VA is volume of the acid 22.65 cm cube times number of moles of the base is 1 all over volume of the base is 25, number of moles of the acid is 2. So this is equals to, I can move further now to just get my answer out. 0.1 times 22.65 divided by 50, 0.0453. 0.0453 mole per dm cube. So I have that. Let me be certain. Okay, good. 0.0453 mole per dm cube. This is the concentration of the base. My CB now is 0.0453 mole per dm cube. Okay, next question. Percentage by mass of sodium chloride in the mixture. Now, they are asking us for the percentage by mass of sodium chloride. So they are asking us for percentage what? Impurity. So we have to proceed now to get our percentage impurity. Remember, percentage impurity is the mass count of pure minus the mass count of impure over, percentage impurity. Mass count of impure minus pure over impure times 100, if it is that. So by virtue of that, we need to get the mass count of pure if this one has been given. Good. So that is that, and there's nothing we can do. So we have to proceed by getting the mass concentration of pure. Let's see what we get. Let me take this out. So this is 1, 2, although they did not ask us for that, but we know it is a basic variable required for us to get what we're looking for. So we have to do that first. So let me take that. Mass count of pure is equals to molar count times relative molecular mass. And the molar count is 0.0453 mole per dm cube times 106 g mole. And this is 0.453 times 106 is 4.80. Yes. 4.80 mass count GDM cube. So this is the GDM cube of pure mass count of pure, which is 4.80 GDM cube. So if that is true, let's see how then we can get what they are asking us to do, the percentage impurity. So now I want to get my percentage impurity. I'm going to clean this. Apply the formula, which is mass count of pure minus mass count of impure over mass count of impure times 100. It is important to remember the formulas. It tends to be more by the day when we solve. So the last one is percentage impurity is equals to mass count of impure minus mass count of pure over mass count of impure times 100. The mass count of impure is 6. We have 6 minus 4.8 over 6. Mass count of impure, which is still 6, times 100. And when we use our calculator, we're going to get 6 minus 4.8 over 6 times 100 is 20. This is equals to 20% impurity. So if it is 20% impurity, then the percentage purity becomes what? 80, because 100 minus 20 is 80. So by virtue of this, we've done that calculation. I'm going to move on. Let's take one more question before we move into redox calculations. It is important. Let's take another question. We say A is 0.105 mole per DNQ hydrochloric acid. B contains 6 grams of baking powder per 100 cm cube of solution. Okay. In the titration, an average of 27.48 cm of A neutralized completely 25 cm cube of B. Write a balance equation for the reaction. That's the first thing they're asking us to do. B, we should calculate the concentration of the base in mole per dn cube. The next one, amount of the base in 100 cm cube of B. And the fourth one is the percentage by mass of the base in the sample of baking powder, which is the percentage impurity. So let us begin by listing out the given variables so that we'll be able to get what we want. So I'm going to take these guys out. I think for the first time we're having variables that are different here. The question talked about HCl and sodium hydrogen triacylcarbonate 4. So let me take these out. Okay, so now is sodium hydrogen triacylcarbonate 4. Let me list out the given variables. First, A is 0.105 mole per dn cube. So the concentration of A is 0.105 mole per dn cube of HCl. B is 6 grams of baking powder in 100 cm cube. B, this is the mass count of impure sodium hydrogen triacylcarbonate 4. So let me call it impure. Let's say it's 6 grams in 100 cm cube. So let's move on. In the titration, 27.48 of A, volume of the acid, is 27.48 cm cube of A. Neutralized completely 25 of B. Volume of the base is 25 cm cube. Write a balance equation. So here, before we can even begin to calculate the concentration of the acid of the base in mole per dn cube, the balance equation is essential. Probably that's the reason why they're asking us to balance it, so that we'll be able to know the number of moles of the acid and the number of moles of the base. So now, first question is a balance equation of reaction, which is my HCl plus the sodium hydrogen triacylcarbonate 4 will give us sodium chloride plus water plus CO2. We're going to balance it. Let's check it out. Now we have hydrogen 1, 2. We have 2 hydrogen. Hydrogen is balanced. Chlorine is 1, sodium is 1, oxygen is 3, 2 plus 1, 3, carbon is 4. Okay, it's balanced directly. So we now have the number of moles of acid here to be 1 and the number of moles of base to be 1. So by virtue of this, we have balanced the equation. We've answered the first question. So the next question they are asking is we should calculate the concentration of base in mole per dm cube. So for us to do the calculation for the base in mole per dm cube, we need the formula. So remember we have about 3 formulas for molar concentration. Molar concentration is mass con over relative molecular mass. Molar concentration is amount over volume. And molar concentration also is the CAVA. Of these 3, the only one that is that we can make use of is the CAVA, because the CA is given and the CB is not given. So we will make this a subject, then we can proceed further. So let me list them out. So to the con of B, we use the formula CAVA over CBVB is equals to NA over NB. Then we're looking for CB, so CB will become CAVA-NB over VB-NA. And this is equals to the concentration of the acid is 0.105 mole per dm cube. Volume of the acid is 27.48 cm cube. NB, number of moles of the base is 1. All over. Volume of the base is 25. Times number of moles of the acid is 1. And this is equals to, so when we use our calculator, this is what we get. 0.105 times 27.48 divided by 25. This is 0.115. So I have 0.115 mole per dm cube of B. So I can now say CB is 0.115 mole per dm cube. First thing first. So the third question says we should calculate, where is it? We should calculate the percentage by mass of the base in the sample of baking powder. So we want to look for the percentage impurity. Now remember, percentage purity is mass count of pure over mass count of impure times 100. That of impurity is mass count of impure minus pure over impure times 100. So it is important that for us to be able to use that to get the percentage impurity, we must have to get the mass count of pure. That one is certain. So, but that of impure, they give us in a shallow way, which means we are not done. We have to complete this, then before we can get the other one. But all things being equal, we're going to state the both of them and see how we do that. So I want to take these two out so that we can proceed. All right, let me start by getting the mass count of impure. 3. Mass count of impure B. So remember, mass concentration can also be molar count times relative molecular mass, and it can also be mass over volume. So in this case, that of impure, they're giving us the mass and the volume. So that's the one we're going to use. So we have mass over volume. Mass is 6 grams. The volume is 100 over 1000. Now, how do we get the 1000? Remember, I said earlier on, the volume for this formula, which we say mass count is mass over volume, the volume is in dm cube. So for us to be able to convert anything to dm cube, we divide it by 1000. So that's how we got that. So now I have my 100 divided by 1000, I have 0.1, which is the same thing as this, and this 1 divided by 10 is 0.1. So now I have 6 gram over 0.1 dm cube, and this will become 6 over that. So 6 divided by 0.1 is 60, very high, 60 GDM cube of impure B. So now this is finally 60 GDM cube. That was very, very high. So now let's move on and get that of mass count of the pure sample. This is the mass count of the impure sample. So the fourth question now becomes, mass count of pure B is equals to molar count of B times the relative molecular mass of B. So the molar count of B is 0.115 mole per dm cube times the relative molecular mass. Yes, sodium is 23 plus hydrogen is 1 plus carbon is 12 plus oxygen is 16 times 3. So this is 24, 34, 36 plus 48. This is 70, that is 80 watt. Alright, let me just go through it, all of it. So I have 16 times 3, which is 48, yes, plus 12, plus 1, plus 23, good. Now I have my 16 times 3 is 48, yes, plus 13, which is these two, then plus 23. It's 84. So everything here is 84. So I'm going to have it this way, 0.115 mole per dm cube. So 0.115 mole per dm cube times 84 g mole. That becomes 84 times 0.115 is 9.66. This is 9.66 GDM cube. Okay. Now we go, that of pure is 9.66 GDM cube. And finally, they say the percentage impurity. Now we have the variables required, so we can substitute to get what we want. So let me take this out. Okay, the last one, which is 4 or 5, something like that. Percentage impurity is equals to mass count of impure, 60 GDM cube. Okay, minus mass count of pure, which is 9.66 GDM cube, over the mass count of impure again, which is 60 GDM cube, times 100. So I can say 60 minus 9.66 divided by 60 times 100. That is 83.9. 83.9% impure. The rate of impurity is very, very, very high. So that is it. We've been able to do justice to the needful. So now it seems we're going to take a question on redox, so that I'll be able to see how to deal with redox. When any question come on redox, we're not going to be too off, as to say, not prepared. So I've given us the formulas for redox. We're going to apply them here also to see how much we can do, what we can do about that. So let's take our first question on redox. Let me clean the board then. Okay, say A is a solution of KMnO4, which is potassium tetraozomanganate 7. B is 0.02 mole per dn cube of ethane dioic acid and solution. C is 1.0 mole per dn cube of concentrated H2SO4. If 25 of solution B gives 16 of A for complete oxidation, from the equation of reaction below, which they've given to us, we should make the following calculations. Let me state out the given. A is KMnO4. This is the oxidizing agent. B is H2C2O4. This is the reducing agent. So, I don't know. I feel like using, instead of A, I'll just call it O. O is oxidizing agent because this is redox titration, which focuses on oxidizing and reducing agent. So when we use A, sometimes we may be confused calling it A for acid, okay? But then, if we remember what it is, I think we're going to be fine. Let me call this O, oxidizing agent, and R, reducing agent. Now, if R is KMnO4, B is 0.02, B which is, okay, this is 0.02 for the volume of reducing agent. So we call, concentration of reducing agent. Concentration of reducing agent. We call it 0.02 mole per dm cube. And what variable again? If 25 of B, which is supposedly a reducing agent, the volume of reducing agent is 25 cm cubed. Give 16 of A, volume of oxidizing agent is 16.5 cm cubed for complete oxidation reaction. From the equation of reaction, so let's write out the equation of reaction, which they give us. We have 2 MnO4 minus plus 5 C2O4 2 minus plus 16 H plus will give us 2 Mn 2 plus 10 CO2 plus 8 H2O. So this is quite different from the usual. Alright, we've not solved any of these, but I've given you the formula, so I owe you to solve it. So now let's put down the number of moles of oxidizing agent is 2. Number of moles of reducing agent is 5. Okay, we've gotten that now. We should calculate the concentration of O, which is O in mole per dm cube. We want to calculate the concentration of the oxidizing agent in mole per dm cube. Remember, we have that of the reducing agent over there, and this is that of the oxidizing agent we don't have, so let me put it here. Concentration of oxidizing agent is what? This is capital C. It's important. So 1 molar con of O, oxidizing agent. We use the formula COA VOA over CRA VRA is equals to number of moles of oxidizing agent or number of moles of reducing agent. Concentration of oxidizing agent times volume of oxidizing agent. The other one is concentration of the acid times the volume of the acid over concentration of the reducing agent times volume of reducing agent equals to number of moles of oxidizing agent over number of moles of reducing agent, OA and RA. Now we want to make the oxidizing agent, concentration of oxidizing agent, the subject. So I can now say this is equals to concentration of oxidizing agent will therefore become the concentration of reducing agent and the volume of reducing agent times number of moles of oxidizing agent over volume of oxidizing agent times number of moles of reducing agent. And that is equals to, let's substitute the variable. Concentration of the reducing agent over there is 0.02. So this is 0.02 mole per dm cube times volume of reducing agent is 25 cm cube times number of moles of oxidizing agent, number of moles is 2 over volume of oxidizing agent. The volume of oxidizing agent is 16.5 cm cube times number of moles of reducing agent is 5. This is 5. So let's proceed. So I have 0.02 times 50 divided by 16.5 and 5. 0.0121. 0.121 mole per dm cube. So now I've gotten 0.0121. Okay, good. Oh, sorry, that's not true. 0.0. 0.0121. Okay, good. So now we have the concentration of the oxidizing agent. Let's look at the concentration of solution B in GDMQ. That is, B is reducing agent. We want to look at the concentration of the reducing agent in GDMQ. Reducing agent, which is ethane dioxide, the concentration in GDMQ, which is the molar count times the relative molecular mass. So we're going to find out what the relative molecular mass of this compound is, multiply it with the molar count which is given. So here I have 0.0121 mole per dm cube. So now I can clean out the board now. Now, second question, count of R in GDMQ. And this is equals to the molar count times the relative molecular mass. The molar count is 0.02 mole per dm cube. The relative molecular mass is 90 g mole. Now, how do we get 90? H2C2O4, 1 times 2 plus 12 times 2 plus 16 times 4. 64 plus 24 plus 2. 60, 70, 80, 88, 90. So that is how we got this 90. Now let us finalize to get the mass concentration of that. 0.02 times 90 is equals to 1.8. This is 1.8 GDM cube of R, which is supposedly B. Okay, the next question says amount of O in the average volume of A used. Yes, the amount of O in the average volume of acid used. Let us see how to do that. So I'm done with this, and that's my answer. So let's proceed to get the amount. The third question. Now, amount of O and the average value of the O used. Now, what is the formula for amount? Amount, it can be mass over relative molecular mass. Amount can also become molar count times volume, and the volume is in dm³. So amount, which we say now, becomes molar count times volume in dm³. The molar count of this is 0.0121 mole per dm³ times the volume is 16.5. 16.5 over 1000 dm³. And this is, why is it 16.5 divided by 1000? Because we're converting it from cm³ to dm³. We divide by 1000. So 16.5 divided by 1000 is this. So I have, excuse me, I have 0.0121 mole per dm³ times 0.0165 dm³. So when we multiply the dm³, the volume, and the molar count, what are we going to get? So 0.0165 times this times 0.0121 is equals to 1.99, okay, or we'll call it 2.0, whatever it is, 99, leave it like that, times 10 raised to the minus 4 mole. This is the amount. It is important. You do not forget that. So probably we're just going to solve maybe one more or two more questions and call it a day. All right, let's see another question here. This one is on water of crystallization using Redox. So probably it's important. If we solve this, it's important. You don't know which one will come. So just get ready, anyone you see, and probably take one as assignment and see what we get. So now let's go. Let me take this out. Okay, the question says 0.02 mole per dm³ of KMnO4 react with 27.52 gdm³ of iron sulfate X hydrate and 25 cm cube of the reducing agent react with 25.60 of the oxidizing agent. If the equation of reaction is given below, we should calculate the number of moles of water of crystallization, calculate the percentage of water of crystallization, and calculate the percentage of iron 2 in iron sulfate heptahydrate. So let me not tell us what it is until we get there. So let's begin. Our next question here says, this is our given. Write it as given. We have O, oxidizing agent, which is concentration of oxidizing agent is 0.02 mole per dm cube. And the oxidizing agent is KMnO4. React with 27.52 GDM cube or B of arrow. So let's call this arrow, which is SO4.x water. We don't know what that is, the X. 27 of this and 25 of the reducing agent. The reducing agent is 25. The volume of the reducing agent is 25 cm cube, while the volume of the oxidizing agent is 27.52. Oh, this is not the volume. This is the mass concentration. It's 25. Let's call it the volume here is 25.60 cm cube. Okay. If 27.52 GDM cube of this. So this guy is the hydrated, the mass concentration of the hydrated. Okay. GDM cube or hydrated is 27.52 GDM cube. All right. If the equation of reaction is, let's see the equation, which is MnO4 minus plus 5 Fe plus 8 H plus give us Mn2 plus 5 Fe3 plus 4 H2O. So from the equation of reaction given here, we'll be able to know what the number of moles of the oxidizing agent are. Number of moles of oxidizing agent will be 1. While the number of moles of reducing agent, number of moles of reducing agent is 5. So I can easily take this out. Now, this is my question. Now, what's the next question? They say the number of moles of water of crystallization, which is X. That formula says that mass con of hydrated over the relative molecular mass of hydrated is equal to the mass con of anhydrous over relative molecular mass of anhydrous. That is the formula for us to get our X. But in order for us to do that, we must know the mass concentration of the anhydrous. So how are we going to do that? The mass concentration of the anhydrous will come how? Molar con times relative molecular mass. And with the molar con is not given. So the molar con of the reducing agent is not given. Which means we must have to first of all calculate the molar con of the reducing agent. Then we calculate the mass con from there before we can answer the question, which says the number of moles of water crystallization. You see that the question is not a direct question. There are other parameters that must be gotten before we get to where we are heading to. But we must have a further knowledge of what we're dealing with. Otherwise, we're going to be lost at the point. So let's proceed to get the molar con of this first. Then when we get that, we get the mass con, then we proceed. All right? Let me take this. So 1 molar conc of R, reducing agent. For us to get the molar conc of the reducing agent, we're going to use the formula COA VOA over so on and so forth, CRA. So now let's proceed. This is what we get. Concentration of oxidizing agent times volume of oxidizing agent over concentration of reducing agent times volume of reducing agent is equal to number of moles of oxidizing agent over number of moles of reducing agent. Now, let me proceed. We're looking for the CRA, which is this. So, my CRA will become COA, concentration of oxidizing agent, times the volume of oxidizing agent, times the number of moles of reducing agent, over the volume of reducing agent, okay, this volume of reducing agent times number of moles of oxidizing agent. It's important, the formula can be confusing sometimes. So we have COA, VOA, NRA over VRA, NOA. So this can therefore become the COA, concentration of the oxidizing agent, is 0.02. So this is 0.02 mole per dm cube times volume of oxidizing agent is 25.63 or 6 cm cube times the number of moles of reducing agent, alright, is 5. This is equals to the volume of reducing agent, of reducing agent is 25 cm cube times number of moles of oxidizing agent is 1. So this is equals to, so if we check that out, this is what we're going to get. We have 0.02 times 25, 0.02 times 25.6 times 5 divided by 25. This is 0.102. 0.102 mole per dm cube. So this is the concentration of the reducing agent. So I can now say CRA is 0.102 mole per dm cube. Good. So that we've gotten, I can take the formulas out, this and the equation, so that we know what we're doing. Now we've gotten the concentration of the reducing agent, and the next thing to do, we want to get a mass conc of the anhydrous. They've given us that of hydrated, so we want to get a mass conc of the anhydrous R. So let's see. This is of hydrated GDM cube of anhydrous is what? That's what we want to get now. So from our equation of reaction, or from our formulas which we know, mass concentration is molar conc times the relative molecular mass of the anhydrous. So we're going to see that. So let's take our next question, which is 2. Mass conc of anhydrous R will become the molar conc, which is 0.102 mole per 52 times 0.102 will give us 15.5. So this is 15.5 GDN cube. 15.5 GDN cube. Alright, that is now our answer. So now we can put in everything to get what we want in the formulas for number of moles of water of crystallization. So I can proceed right now. Let me take this out. Now, 3, which is number of moles of water of crystallization. Number of moles of water of crystallization. Now, for us to do that, we say relative molecular mass of hydrated over mass con of hydrated is equals to relative molecular mass of anhydrous over the mass con of anhydrous. Now, the relative molecular mass of hydrated is 152. I think that was what we did. Let me check that out. I say 56 plus 32 plus 64 is 152. Now we have hydrated is 152 plus x18 over water is 18. The relative molecular mass of water is 18. So that's why we're having x18 over the mass con of hydrated, which is 15.5. 15.5 is equals to the relative molecular mass of anhydrous, which is this alone, is 152. Mass con of anhydrous is 15. Oh man. Of anhydrous is 15.5, not the other one. 15.5. Hydrated was given to be 27. So it's 27.52. 27.52. Okay. From here, we're going to make x the subject of formula. When we make x the subject of formula, whatever we get becomes the number of moles of water in the sample. So now let me clean some of these things so I can get there. Okay, by making this the subject means I should use this to multiply first. So I will have 15.5 outside, open bracket, 152 plus x18, short my bracket, is equals to 27.52 times 152. Now we go. 15.5 times 152. 15.5 times 152 is 2356. 2356 plus 15.5 times 18 is 279x, because there is x here, and this is equals to 27.52 times 152 is 4183.04. Now, if I have to make my x the subject, I will have 279x is equals to 4183.04 minus 2356. Okay, let's check that. This minus 2356 minus 2356 gives us what we have here. So I have 279x is equals to 1827.04. Divide both sides by 279. 279. This will go, my x becomes, that divided by 279 is equals to 6.5. 6.5. X to the nearest whole number is 7. So if x is 7, it therefore means the name of the compound becomes, the formula becomes FeSO4 7H2O. This is what it is right now. The name becomes iron 2 sulfate or iron sulfate heptahydrate. That is the name. So in case you are being asked, you should not forget that. It's important. So we've gotten X. Remember, when we started this whole thing, they asked us of only X. What is the number of moles of water of crystallization first? But all of these calculations we've done in the previous are just preambles to take us to where we are heading to. So the question many a time may not be straight, but we must understand the cognitive aspect of it in terms of application to get what we want. If we fail to do the basic things or to put these things into practice, then it will become difficult for us. So, you see the number of moles of water of crystallization that we've gotten. Now we should calculate the percentage of water of crystallization. So the next question is the percentage. So let me take this out, which is 7. We have that. The next thing is percentage of water of crystallization. Okay, 2, percentage of water of crystallization, blah blah blah, is the value of the water, which is 7H2O, over the total compound, which is this 7H2O times 100. Now this is 7 times 18 over 152 plus 7 times 18 times 100. And this is 7 times 18 times 18 is 126. So now I have 126 over 126 here too plus 152. Okay, which is 278 times 100. And finally, the percentage of water of crystallization is 126 divided by 278 times 100. The percentage is 45.3%. 45.3%. Next, the percentage of iron in this whole compound. So the percentage of iron will become, that's 2, will become iron over iron sulfate dot 7 moles of water times 100. Iron is 56 over 152. Yes, 152 plus, what was that? 7 times this is 126 plus 126. The 126? Yes, 126 times 100. And this becomes 152 plus 126. 152 plus 126 is, let me come again. 152 plus 126, which is 7 times 18. 126 is 278. So now I have 56 over 278 times 100. And that finally becomes 56 over 278 times 100, and that is 20.1%. So the percentage of iron is 20. That of water is 45.3. So this sulfur and oxygen, if you calculate them and add all of them, you get 100. That is what it means. So we have done justice so far in calculating using the basic principles of volumetric analysis and their formulas to calculate a broad spectrum of calculations in terms of percentage purity, percentage of water of crystallization through what? Redox, by the application of what? Redox. And we've done that in this term. I don't know, probably if I should do one last, this is on water of crystallization. Let me use Redox to solve the last one that has to deal with percentage purity, and we can shut down there if we want to, and also take some questions as assignment. So it is important, if you remember the formula, you do a lot. If you don't know the formula, you can't do nothing. So it is important you go back to my third video, if not mistaken, on volumetric analysis calculations in my channel. You're going to see all the formulas, then master them and put them into practice by solving most of these things. Wherever you have any problem you do not understand, you can always send your comment to the comment section. I will check them out. Where you have hindrances, I will sort them out for you. It is important as such. So let's proceed again and take the last question for the day. Let me see. Something that wouldn't take us too much time. All right. This is our last question for today. Good. 0.019 KMnO4 react with 6.0 GDMQ of impure ethane dioxide solution. So KMnO4 is the oxidizing agent. So I have my O, KMnO4, and the concentration of oxidizing agent given is 0.019 mole per dm3. So react with 6.0 GDN of impure ethane dioxide. So my reducing agent R is H2C2O4. That's ethane dioxide, and its GDN of impure is 6.0 GDNQ. Let's proceed. Okay, 25 of ethane dioxide. Okay, that is the volume of reducing agent is 25 cm3. React with 23.50. The volume of oxidizing agent is 23.50 cm3. If the equation of reaction is given to be, so let's see the equation of reaction they give us here. It's given to be 2MnO4 minus plus 5C2O4 2 minus plus 4 hydrogen plus will give us 2Mn 2 plus 10 CO2 plus 8 H2O. Now, the balancing of redox reaction, I have a video uploaded how to balance this redox. It's a complex reaction that it takes a lot of time, patience to study. But I have done that. I've solved a whole lot of balancing equations in my channel. You can always find out how these things are done. I'm not teaching about balancing today, so I wouldn't teach you how this is done. It has some series of steps, about 4 or 5 steps to take. So you should find out, go check it out in my channel. So this has been given. Let's proceed from here. Now the number of moles of oxidizing agent is 2. And the number of moles of reducing agent is 5. So from the equation of reaction, we're able to get that. Now, question number 1. It says, calculate the percentage impurity. Oh, that's just a straightforward question. They gave us just one question. We should calculate the percentage impurity. So in our course of solving it, you will understand that there are a whole lot of other things we should know before we can go down to that. And many times you may likely be encountering such questions. Calculate this. Meanwhile, there are a series of things you should do before you get to that. So for us to get the percentage impurity, let us come back to reality. The formula for percentage impurity states that mass count of impure minus mass count of pure over mass count of impure times 100, which means we must know the mass count of pure. So that is given for the mass count of impure. So we can proceed to get the mass count of pure. How do we do that? Now, for us to get the mass count of pure, we must first of all know the molar concentration of the reducing agent. So we have to first calculate the molar concentration of the reducing agent. Then we apply mass count to be molar count times relative molecular mass. Then we can now bring in the other formula. So that is it. The first thing to do is to calculate, number 1, molar count of R, which is the reducing agent. For us to do that, we use the formula, the concentration of oxidizing agent times the volume of oxidizing agent over the concentration of reducing agent times the volume of reducing agent is equal to the number of moles of oxidizing agent over the number of moles of reducing agent. So if I make the concentration of the reducing agent of which I'm looking for, the subject, I will have, I'm making concentration CRA the subject, I will have concentration of oxidizing agent times the volume of oxidizing agent times the number of moles of reducing agent over the volume of reducing agent times the number of moles of oxidizing agent. So I will substitute the variables into that formula. Concentration of reducing agent will therefore become, when I substitute, the concentration of oxidizing agent is given to be 0.019. So I have 0.019 mole per dm³ times the volume of oxidizing agent is 23.50 cm³ times the number of moles of reducing agent there is 5. This is all over. The volume of the reducing agent is 25 cm³ times the number of moles of oxidizing agent. Number of moles of oxidizing agent is 2. So this is equals to what? Now I have 0.019 times 23.5 times 5 divided by 50. 447 is 0.0447 mole per dm³ of R. So I will say now CRA is 0.0447 mole per dm³. Next question is to get the mass count of the pure ethane dioxide acid. So let me take this out now. Now, mass count of pure pure R, we now have it to be molar conc times relative molecular mass. The molar conc is given to be 0.0447 mole per dm cube, and the relative molecular mass is 90 g mole. I've calculated this before, how we got 90 from here. 64 plus 12 times, 12 times 2, which is 24. Carbon is 12, yes, times 2, 24, then plus 2, we get 90. So this is, the mass conc is therefore, that times 90 is 4.02. So 4.02 GDM cube of R. So the GDM cube of pure is 4.02 GDM cube. Now, if that is true, our last move now becomes, we should calculate the percentage, where is it? So we should calculate the percentage impurity. Now I want to know the percentage what? Impurity. So we just move straight up, apply the formula, and off we go. The percentage impurity therefore becomes, let me take this out so I can do that. Now, the last question here, 3. Percentage impurity is gotten through the formula. We say the mass conc of impure, which is 6.0, minus the mass conc of pure, which is 4.02, over the mass conc of impure, 6.0, times 100. And this becomes 6 minus 4.02 divided by 6 times 100 is 33. So this is 33% impure. So that's that. Remember, they asked us just a simple question. We should calculate the percentage for impurity. And we know in the course of us doing that, we must have to go all the way around to know the molar concentration, the mass concentration, and all of that. So that is where we are. So we're going to take, we've done justice to the basic things which we should know or do. I'm just going to give us one question, which should be like an assignment. So I will read it, I'm not writing it. So just take note of it, it's important. You submit it when I ask you to. Probably solve it, yes, and upload the answer for me. It says that if KMnO4 of solution O stands for oxidizing agent, react with 0.1 mole per dm cube of, I am going to write this, ammonium sulfate, iron sulfate, hexahydrate. Let me clean the box so that it will be distinct. Okay. You react with NH4, SO4 dot iron SO4 dot 6H2O. This is one compound. And that's the only question left in the book, so you're going to solve that. If KMnO4 solution O for oxidizing agent react with 0.1 mole per dm cube of the reducing agent, this, as solution R, and 25 of R gives 24.5 cm cube of O for oxidizing agent. If the equation of reaction is given to be, okay, let me give us the equation again. The equation of reaction is MnO4 minus plus 5 iron 3 plus 8 hydrogen plus gives us Mn2 plus 5 iron 3 plus 4 H2O. Now the number of moles of the oxidizing agent is 1, that of reducing agent is 5. Take note of that. Now, it says that if the equation of reaction is this, you should calculate the molar conc of O, the mass conc of O. The molar conc is the molar conc of the oxidizing agent, the mass conc of the oxidizing agent, the mass conc of R, which is the reducing agent, amount of R in 1 volume of R used. So amount, the formula for amount is straightforward, you know that. We have amount is mass over relative molecular mass, and amount can also be molar conc times volume in dm³. So any of these you should apply. So we're going to stop here for today, and we've done justice to the basic things we should do. For those of you who have not subscribed, I still don't know what you're waiting for and why you are still lacking behind. There are a whole lot of information passing by that you should get in tune with. It is imperative that when you subscribe, you press the notification bell so that whenever I upload a video, you're going to see. Like the videos when you watch them. Send your comment to the comment section. Ask your questions when necessary. I will attend to them all. I'll see you when I see you again. Thank you.